Hi, and welcome to the first video on DC circuits. Before we jump right into the nitty-gritty electronics, I just want to hit on a couple of points from physics that explain why things work the way that they do. No math, and it's just a couple of minor points. Should just take a couple of minutes. And bear in mind that I'm leaving out a ton of information for ease of understanding and just what's pertinent to us. So this is not 100% accurate. I'm assuming by now you've at least seen the periodic table of elements, even if you haven't studied it. There isn't much on here for us, but we do need to take a quick look. The table lists all 118 elements that we've either discovered, invented, and a few that we've just theorized must exist. If you were looking at the real table, you would notice in the upper left-hand corner of each element there's a number. The numbers listed are the atomic number of the element. For example, if we look at an element such as gold, the first thing we consider is, why is it listed as AU instead of something a little bit more pertinent? A dollar sign, maybe. Anyway, in the corner, we see that gold has the atomic number 79. This number is not assigned arbitrarily, or gold would probably be number 1. Now, this is the number of protons gold has in the nucleus of its atom. If we were to add another proton, we wouldn't have gold anymore. Instead, we would have mercury, which has 80 protons. Removing a proton would transmute our gold atom into a platinum atom. Both of these transmutations are very difficult to pull off. In fact, to do it in any kind of quantity takes no less than the core of a star. And even that craps out at iron, which is element 26. Every naturally made element above that has to be created in a supernova. At the bottom, you'll find the atomic weight, which means nothing to us. But on better tables, there will be a description of the valence band of electrons. This one says that it's based on xenon and has a single electron in its valence band. The valence band is where all the action happens for an atom, both chemically and electrically. If we look at the solar system model of the atom, which is an apt description for what we're working on here, we'll find in the center, the nucleus, is where all the protons are clumped together, and this is orbited by all of the electrons. Notice instead of a single planet in an orbit, in the atom, the electron shells have multiple electrons in each orbit. The first shell, the innermost, can hold up to 2 electrons. The second can hold 8 more. The third adds 18 more. And the next can hold 32. One of the key things to note is that electrons always want to be as close to the nucleus as possible. So the inner shells always fill up first. Now, it's true that a stray photon can bump an electron up into a higher orbit, but it will just as quickly drop that energy and go back to its normal place. Looking back at our gold atom, you'll see that the inner shells are totally full, and the outer shell, there's just a single electron in it. This is the valence band. As I said earlier, this is where all the action happens. Although the protons are what make this gold, it's the electrons in the valence band that interact with all the other atoms around it. So let's take a quick look at what makes these electrons tick. I'm sure everyone's familiar with magnets and that there's a magnetic field that connects the north and south poles of the magnet. And that magnets resist connecting 2 similar poles, so you can't connect them south to south or north to north. But they readily snap right together when the north of one magnet comes close to the south pole of another magnet. This is the old adage, like poles repel and opposites attract. Now, magnetism and electric charge are really just 2 sides of the same coin. You can use electricity to create magnetism, or magnetism to create electric current. In fact, these 2 forces of nature are so entwined that physicists have stopped referring to them as separate forces altogether and just refer to them as the electromagnetic force. In the case of charged particles, though, there is not an opposite end. The protons have a positive electric charge, and the electrons have an equal but opposite negative electric charge. And these charged particles use the same rules. Similar charges repel and opposites attract. So no two electrons ever want to get close to each other, nor do two protons. But the attraction of opposite charges is what sucks the electron into the atom and their desire to crash into the protons. It's just some other rules of physics that prevent that from ever happening. Just as it takes a bunch of neutrons and the strong nuclear force to overcome the natural repulsion of all those protons stuck together. Lastly, it's important to note that some of the electrons in the outer bands can be what's termed loosely held, which means that they can drift away from their host atom and move on to another atom. These are referred to as free electrons, and the atoms are referred to as ions. And this effect is called electron drift. It's important to note that there's no real direction to electron drift. It just happens randomly in any direction. What's very relevant about this now is that elements that have a great amount of free electrons can conduct electricity very easily and are thus called conductors. Materials that have little or no free electrons resist the flow of electricity, and we call them insulators. Some of the best room temperature conductors include silver, copper, aluminum, and gold. And the best, or some good insulators, are paper, plastic, rubber, and glass. I know this was the long way around, but sometimes it helps to understand why things are happening rather than just knowing that they do. But here's what you need to take away from this video. Electrons and protons are attracted to each other, but will repel each other, or will repel similarly charged particles. Some materials make good conductors and others make good insulators. But just to be clear, at anything near room temperature, there is no perfect conductor. Everything resists the flow of electricity at least a little bit. So this is the end. Join me next time where we'll be jumping in and looking at some schematic diagrams, batteries, voltage. And don't forget to hit like if you did, and to subscribe if you want to keep up to date at what we're doing. Thank you. Bye.